Uh, Good afternoon, everyone. Today I will talk about the node generation of synthetically feasible molecules. One of the tasks of cheminformatics is a search for new molecules with desired properties. This can be achieved by a virtual screen or virtual existing libraries. However, any existing or enumerated library will represent only a tiny portion of the whole chemical space, which is estimated as 10 in power 33 molecules. Therefore, systematic exploration of the whole chemical space is currently unfeasible, but it can contain hidden treasures which we want to discover. The Novo design suggests an alternative strategy to explore chemical space. It performs an adaptive search of molecules which would satisfy given properties. Traditionally, this search is iterative and consists of 3 repeating steps. On the first step, structures of molecules are generated, and they are evaluated by a model or models. And on the third step, most promising molecules are selected for the next iteration where they will be modified and so on. This cycle is repeated until we get a desired number of compounds satisfying given criteria. There are 3 main groups of conventional approach for structure generation. One is atom-based, where molecules are constructed by adding or removing atom and bonds. Reaction-based approach constructs structures from supplied building blocks using the set of predefined reaction rules. And fragment-based approach constructs molecules by linking or replacing fragments. Approaches using machine learning can directly generate compounds by sampling their structures from the preferable latent space. This is a very appealing strategy, but the generated molecules are not always synthetically accessible, like in the given example from one of the first publications on this topic. Traditional structure generation approach also suffered from issues with synthetic accessibility. Even a reaction-based approach cannot guarantee it. Here's an example from the recent publication of Aftergrow 4, where authors designed PRP inhibitors guided by molecular docking. Structure word generation using reaction rules and genetic algorithms. The final top-scored molecules look quite complex and not very feasible. So currently the major issue of the Novo approaches is a structure generator which can consistently generate synthetically feasible molecules. Recently in our group, we developed a fragment-based structure generator CREM, and within the current study, we implemented a workflow to autonomously explore the chemical space using CREM guided by molecular docking. We investigated this approach on the task of searching for inhibitors of CDK2, which is frequently used in analogous studies for benchmarking. Finally, we tried to apply this workflow for the task of fragment extension in the search for inhibitors of the main protease of SARS-CoV-2. To assess the synthetic accessibility in our work, we use a model proposed by Peter Eltel. It returns values in the range from 1 to 10, where 1 means easily accessible molecules, 10 is difficult to synthesize. Here you may see example of molecules from Campbell with corresponding assay scores. The top scored molecules, which was designed by Aftergrow as PRP inhibitor, has a score 4.6, which also supports our suggestions about its poor synthetic accessibility. The approach we are developing of the Novo design is based on the previously proposed CREAM methods. Within CREAM, previously synthesized compounds are exhaustively fragmented, and for each fragment, the nearest environment of a fixed radius is determined. The fragments and associated environments are stored in the database, if we can see on the slide. If we want to replace in particular fragments, if we want to replace a particular fragment in a parent molecule, we determine its environment and search for fragment associated with the same environment in the fragment database. If corresponding fragments are found, we perform these replacements. The generated molecules will always be chemically valid, and we can control its synthetic feasibility by tweaking some parameters. It was previously demonstrated on a set of ligand-based benchmark tasks from guacamole suite that using fragment libraries generated from more synthetically accessible molecules leads to more feasible generated molecules. Similar effect can be achieved by choosing a greater context radius that makes replacement more conservative and less numerous. We will evaluate this hypothesis in structure-based generation conditions. Like other conventional approaches, our approach also implements the iterative strategy of chemical space exploration. On the structure generation stage, we use CREM to replace hydrogen atom of parent molecules. Since the number of possible replacements are usually very large, and we restrict the generator to make up 2,000 random replacements with fragment have from 1 to heavy atoms. And afterwards, compounds may be filtered by particular physicochemical properties and docked into the protein. As an objective function, we can use the raw docking score only, and we can use more complex functions, which include other parameters set by a user, for example, drug likeness or lipophility. After the docking stage, we may filter compounds by their observed protein ligand contacts to restrict the search to ligand interaction with particular residues. Afterward, we select some molecules to pass them to the next iteration. This can be made in a greedy manner by selecting top scored compounds. However, this may result in low diversity of output structures. Therefore, we implemented two other protocols. One uses Pareto ranking with two parameters, score and molecular weight. We select molecule lying on the Pareto front and have low molecular weight and high docking score. This would propagate promising molecules having low molecular weight to late iteration and give them a chance to grow. Within the other selection strategy, we cluster molecules on a given number of clusters and select top scored compounds from clusters. This procedure is repeated until we cannot grow molecules anymore because they exceed physicochemical parameters. As a target for benchmarking, we choose a complex of CDK2 with a highly active inhibitor. Since for kinase inhibitors, interaction with the hint region is important, we restricted all our generation runs with this condition. Molecules should interact with this hinge region. In the initial runs, we wanted to study the effect of a chosen fragment database and context radius on docking score of generated molecules and their synthetic accessibility. The following parameters were kept fixed. We use these constant conditions, and for the selection stage, we choose a clustering algorithm with 25 clusters and selecting top 2 scored molecules from each one. We run simulations with every combination of input parameters 3 times to investigate the effect of random fragment selecting growing. On the plot, you may see the average docking and SR scores for top 100 molecules obtained in each run. Databases are indicated by shape, and colors indicate the context radius. We may notice that runs using a large context radius results in highly similar output in terms of docking and SR scores. And we counted the number of identical structures generated in different runs and found that generation with a large radius frequently resulted in identical compounds from 50 to 90%. This trend was observed for all fragment databases, even for the least restricted one. This indicates that the number of replacements is very limited for the large radius and random selection of 2 thousand replacement result in almost the same fragments. We established that docking scores of top scored molecules mainly depends on the chosen context radius and substantially drops with its increase. At the same time, we chosen fragment databases less affect the docking scores and frequently result in molecules with comparable score values. As a score turned out to be more sensitive, it depends both on the radius and fragment databases. The greater the radius, the more synthetically feasible compounds are generated. The similar effect is observed if we use more restricted fragment databases obtained from synthetically more feasible molecules. You may see examples of top-scored molecules for some of the runs. For further simulation, we have to choose a setup which results in high synthetically accessible molecules with lower docking scores, since the lower docking scores are better. The solution creates a Perta front, and from which we selected the setup using radius 2 and fragment database generated from Campbell molecules with SR scores up to 2. As it results, it's a reasonable trade-off between docking and SR scores. This setup will be fixed in the following runs. We studied the effect of the chosen selection approach on diversity of generated molecules. The use of different selection methods lead to some variation in docking scores, but the SR scores were changed insignificantly. To evaluate structural diversity, we counted the number of distinct Murko scaffold in top 100 scored compounds in different runs. These values are depicted on a diagonal of the heat map. As we can see, the greedy strategy resulted in the lowest number of distinct scaffolds, and they were mainly reproduced in individual runs, if we can see. The clustering approach resulted in a slightly greater number of distinct scaffolds, which frequently differ across runs. The Pareto front selection achieves the highest diversity of enumerated molecules, about 60% of distinct scaffolds. At the same, the set of scaffolds obtained in different runs almost don't overlap. This suggests that for future studies, one can choose Pareto selection strategy if he wants to get maximum diversity of generated compounds. However, he should be aware that multiple runs may be required because repeated generation may result in substantially better scoring compounds. The influence of objective functions on the drug likeness properties of the generated molecules was also studied. We augmented the docking score with good value, and that resulted in compounds having comparable SS scores but slightly worse docking scores. And however, drug likeness of generated compounds was considerably improved. So this setup can be recommended if we want to bias generation towards more drug-like molecules. There was a heat expansion task to search for inhibitors of the main COVID protease. As part of this task, the structures of the complexes of the main protease with small molecules whose mass didn't exceed 250 daltons were selected from PDB database. Our task was to expand these hits within the binding site in such a way that the parent fragment retains its position and the resulting structure has a high affinity for the protein. This slide shows an example for the 5-RGX complex. The growth process was carried out iteratively. It can be seen how the docking score of the molecule improves during iterations. Overall, we enumerated about 19,000 molecules. Among them, about 1,500 compounds had docking score below minus 8.5 and SS scores less than 3.5. Finally, 11 compounds were selected for synthesis, which was performed by live chemicals. Only 6 compounds were successfully synthesized that resulted in 55% success rate. All of 6 molecules turned out to be inactive. Further synthesis will most likely not be carried out or will be carried out by another company. Within this study, we implemented the workflow for the Novo design of promising molecules and validated it on the benchmark task of searching for CDK2 inhibitors and established the influence of different setup parameters on output molecules. We also applied the implemented workflow to the real case to the DAN inhibitors of COVID protease. Despite inactivity of designed molecules, 55% of them were synthesized. Supports the applicability of the developed approach to the Novo design, which can be further enhanced by incorporating more advanced scoring schemes. I acknowledge all colleagues who contributed to this work. Thank you for attention.
Thank you very much for your talk. We have some questions in the chat. So first question is from Vladimir Borisovich Sulimov. So slide 18.
18, okay.
18. SA score for the top 100 molecules from each run. What does it mean? What is radius or radii? Radius.
Okay, radius is context radius which were used for searching fragments in database to get replacement to change hydrogen from parent molecule to another fragment. We can use other radius. It changed from 1 to 5. And QED, it's drag likeness parameter which used to get value of drag likeness for molecule, how we can use this molecule for our next checking for activity molecules with proteins. Should or not, maybe molecules have high lipophility and we don't use in firstly.
Okay, another question is from Dmitry Filimonov. How much does the final result depend on the initial scaffold?
In our task, we use fragments from Campbell as initial scaffolds. For now, we can't get answer how much initial scaffold influence for our finishing results.
Okay, and the final question is from Dmitry Solodkin. SARS-CoV-2 inhibitors, were they designed as covalent? Was any respect given to the binding sites of pockets?
No, we use non-covalent docking for our docking experiments. And what about binding site subpockets? No, we don't check this. We use only a pocket with initial ligands.
Okay, thank you very much.